Start recording. Alrighty, hello everyone, and welcome to Handmade Hero, the show where we code a complete game live on stream. Yesterday, during the pre-stream, we had a question about, well, not really a question, we had a little quick talk about RLE, and I decided there was some stuff I wanted to show about how RLE and LZ are very similar. So I wrote one yesterday. I wrote an RLE compressor and a little framework for us to use, and we compressed our art asset files with it. And, as we showed yesterday, surprisingly, even a really, really dumb RLE compressor actually compresses our art pretty well. Not compared to a really good compressor, it doesn't, but compared to no compression, it was quite nice. I think it saved 25% of the file size just from our little, really, really bad RLE compressor. And again, I think that's largely because, hey, you got a lot of alpha space in sprites, right? And an RLE compressor can just suck all that up really easily. So it ends up being pretty handy. Anyway, what I wanted to do today was just quickly, for this session, show how a basic LZ compressor, or style compressor, dictionary compressor is really what I should say, is not that different from an RLE compressor, actually. And for that matter, you can sort of just treat RLE, you can basically get RLE out of a dictionary compressor, as I explained yesterday, how RLE just kind of automatically happens in a dictionary compressor because it's just a look back of one or some number, and then it just will repeat that thing. So we kind of went over that as well. Let me go ahead and do that, just show how that stuff works, so now we have it in practice. If you haven't watched yesterday's stream, you definitely want to, because I explained all the stuff about LZ yesterday, so you're going to be a little lost if you didn't hear that explanation when we start here today. All right. So what we did is we built this little compressor, right? Here it is. And I'm going to go ahead, I need my light on here. I'm going to go ahead and build it. I guess I also have to load my project file there. There we go. And our compressor is very, very simple. So you can see here's the entirety of the code for it, right? And all it does is it starts out in main, and it loads. It basically looks to see whether it needs to compress or decompress the file. It loads its first argument after that instruction, and then it either calls the compressor or the decompressor, and then it writes out whatever that thing spit out. If it was a compressor, it writes out the compressed file. If it's a decompressor, it writes out the decompressed file. That's all the main loop does. And then we just have up here our compress and decompress functions, and right now all they do is thunk through to the RLE compressor, because that's what we wrote up here, right? So that's what we got. So here's our RLE compress, here's our RLE decompress, and one thing you will notice, and this is pretty much universally true of every compression thing I've ever seen, and again, as I said many times yesterday, take it all with a grain of salt, because I'm not a compression person, so anything I really say about compression is basic, is beginner stuff. But typically speaking, whenever you look at these, what you generally will see is exactly what this looks like. The decompressor for something is usually very simple, right? It's probably not this simple. For more complicated compressors, it's going to be, not quite so trivial, but it's typically not that big compared to the compressor, which is usually 2-3 times its size. And the reason for that is because usually decompressors, the formats for things are over-specified. And just to give you a little bit of sort of a feel for that, there are some compressors, such as like entropy encoders like Huffman, or arithmetic encoders, RANS encoders, or ANS encoders, I should say, those sorts of things, that are extremely tightly specified. And what that means is that generally there's only one way to encode and decode a particular stream, right? Now that doesn't mean there's not lots of ways you could choose to structure the encoding, right? Whether or not it's adaptive, whether or not you encode it with certain bit patterns, how you're putting certain pieces of data in, all that stuff is definitely flexible. So I don't mean to say that the compressors aren't flexible. What I mean to say is once you pick how all that's done, there's no decisions to be made, right? So when a stream goes into the compressor, it's just churning through it, and it spits out the stream on the other end. And then the decompressor does the same thing. It takes in a stream, churns through it, and spits out the result, right? And what that means is that the compressor and decompressor very often for those sorts of things are not that different in terms of size and complexity, because the compressor doesn't have to think, right? There's only one way to encode the thing coming in, so there's not a lot of thinking that the compressor has to do. Now, with everything else, LZ and MPEG-4 or any of these other sorts of things, typically what happens is the compressor actually has lots of options of how it's going to choose to encode an incoming stream. There are many ways to encode an incoming stream that will all produce the same output stream, right? And that is why the compressor side often ends up being larger and more complicated and involving more sophisticated algorithms than the decompression side, because essentially the compression side is like an AI problem almost, right? It involves like search and, graph traversal and things like this oftentimes to try and figure out what it should be doing and what the most likely thing is that will produce the small-sized signals, the small-sized outputs, whereas the decompressor is just rote. The decompressor is still just one stream in, one stream out, no decisions to make, no thought, right? So typically it always does look like this, and you can actually even see just in our little RLE compressor, which is the stupidest possible thing, right? You can see even there we have all these complex decisions to make. At any given time through the loop, we can choose to output a new literal run pair or not, right? Every time through this loop we're making a decision, should we do that? Now, our decision logic is very, very basic right here and not particularly good. Like I said before, this should probably be a different number, right? But even in this extremely simple case, you can already start to see the asymmetry in complexity of compressors and decompressors, even though we have done the very stupidest thing possible. In both cases, we did the very stupidest thing we could possibly do. We still are already seeing that difference start to appear, right? And it only gets worse. So that's just typically my experience is that it only gets worse as you go further and further down the rabbit hole of compression towards better and better results and more sophisticated algorithms. It's generally the case that, if I wanted to explain to somebody how to write the decompressor for a particular compression algorithm, usually that's the kind of thing you can do in an hour. If you want to explain to someone how to write a good compressor for it, it might take months, right, of study, right? Who knows? That may be an exaggeration, but you get the idea. The compressors end up being sort of very sophisticated and having a lot of complexity to them. So that is basically where we're at with that. So all I want to do now is sort of expand this out to, instead of doing just RLE, doing LZ compression. Now again, we are not trying to make a good compressor here. I'm just trying to illustrate the concept. So this is going to be a very bad LZ compressor, not one that would ever be particularly good. What was the? Oh, I wish I could have seen what inserted in there. Oh, it was the day title from yesterday's stream. I guess it was still in the paste buffer. All right. Anyway, so here we go with our RLE situation. I'm going to just copy this and turn it into LZ decompress. And like I was saying before, really the only difference between RLE and LZ from a base conceptual standpoint is that instead of encoding the thing that we are going to copy as just a single piece of information that we just replicate some number of times, instead what we're going to do is encode an offset that tells us where in the stream to look back to grab the thing that we want to replicate, right? So what we're going to do here instead is, you see this, this is how our decompression for RLE was working before. We were saying, okay, while we still have stuff to ingest, let's take a look at how many literals we expect to see, go through the literals and copy them to the output stream. Then, because we're always doing it in pairs, then we go through and say, all right, what's the rep count and what's the rep value? And then we repeat that value going forwards. Now, so all we're going to do here is change this to like a copy count and a copy value, right? instead, our copy value will now become, well, I guess I can leave it as a U8. Instead of a single value, it's just going to be a distance, right? And so instead of reading in a byte to replicate, we're going to read in a byte that tells us how far back from our current location we want to go, right? OK. Now, what you'll notice here is that the copy distance, we have some choices here if we want to. We can simplify this algorithm a little bit if we want to. One thing we can do, if you take a look at this copy distance, right, and copy count, let's think about what this is going to do. And I guess I can just go ahead and implement it so you can see, right? But here, we're going to need a pointer that's like a source pointer, right? And the source pointer is just going to be, like I said, it's our out buffer minus the copy distance, right? Because if you remember how LZ is supposed to work from this discussion yesterday, we are, well, you know what? If we go here to this disaster, where is it? It's down here somewhere. Right. We're in the output buffer. We're writing to the output buffer. And when we get to a particular location, sometimes we just say, hey, go back to somewhere else in the stream and copy from there, right? So it's all happening in our output buffer. The only thing that we're trying to do here is say, like, OK, when we have that output buffer pointer, which is where we're currently outputting, we just want to start some distance back from there and copy, right? So we say, all right, we're going to start some distance back from there. We're going to go copy count, and we're going to output into the buffer whatever was in the buffer previously at that location, right? Now, again, this is where that subtlety of how RLE can actually be implemented directly in LZ, this is it right here. Because imagine what happens when copy distance is just 1, for example, but copy count is 20, right? Well, what will happen is we'll go back 1 from where we are right now, which means that the last byte we output is now what we're looking at for copy. And then we're going to do it 20 times. So we're going to take a copy of that byte and put it in the current output position. We're going to move the source pointer forwards, which is now pointing at exactly the byte it just wrote, which is a replication of the previous byte. And the process will repeat itself 19 more times, copying that byte every time. So effectively, we get an RLE compressor inside our LZ compressor for free, essentially, right? I mean, and free is probably not the right term because you are perhaps giving up a little bit of encoding for it, but you can kind of see how it doesn't really take any special work to get run length encoding out of an LZ compressor, because effectively, if you just give a larger copy count than the distance that you jumped back, you will replicate, right? And it also allows you to do something that the RLE can't do without additional parameters that would take space to encode, which is you can replicate values that are longer than one symbol, right? You can say, go back 4, copy 8, and that will do 2 copies of the last 4 in the buffer, right? So it can do that sort of a thing. Hopefully that makes sense. All right. So there's our LZ decompressor, and literally that's all there is to it. There's really nothing else that you have to do to implement the decompressor. Again, like I said, it's always the compressor that's the more complicated, so even though that's the only change we made, our compressor is about to get a lot more complicated in order to do anything. Even a really crappy LZ compressor is much more complicated than a crappy LZ decompressor, and so we're about to see that. But anyway, so now you can see how this LZ decompressor works. We do exactly the same thing. We read in a literal count, and off we go. And then we do the same thing we do in the RLE, just copy. And then we do our other stuff here where we take, OK, a copy count, our copy distance, and we perform that copy from somewhere back in the stream. Now, what I was going to say is there's another thing we can do here to simplify this further, actually, and give us a little more flexibility in the encoder. We could have done this with RLE as well, potentially, but it costs more in the RLE to do. And basically what happens in an LZ encoder is, if you think about what's going on here, is we're reading a copy count, and then we're reading a copy distance. OK? That's what we're doing, right? And if you think about what that copy distance is going to be, if the copy distance were to come in as 0, right? So the amount to look back was 0. In that case, we would know that we couldn't possibly be talking about an actual copy, right? Because 0 would not move the pointer at all from its output location, which means that we would be reading garbage because we haven't seen what happens in the stream at that point, right? So in order to not waste one value, which is 0, in the copy distance slot, there's two choices of what we can do. One is we can get an extra byte, of lookback by saying when we read in the copy distance, since we know 0 is invalid, just add 1, and that way instead of being able to look 255 bytes back, we can now look 256 bytes back, right? So we can steal that value to get a little bit further lookback, right? But perhaps more powerfully, in terms of what we will probably expect to get in terms of compression there, is what if instead we just said, well, we're reading a literal count or a copy count, right? What if we just called it a count and we read it every time? And then we said when we read the distance, if the copy distance is 0, then we assume, right, that we're going to be copying literals from the input stream. And if the copy distance isn't 0, then we will do our count, our replication. Right? And that's perhaps a little bit more interesting way to use that value. Now, again, this is not supposed to be some deep insight into LZ at all, because by the time you start doing anything sophisticated with LZ, you're way past the point of thinking about it in those terms anyway. But just in terms of the very simplistic way that we've set it up, you can see that there's an interesting choice there, and it seems like this is probably a better choice given what we're going with. To say like, hey, well, do we really care about just one extra byte of lookback? Instead, we could use that 1 byte to be the thing that switches between our two modes. That way, when the encoder wants to encode things, it doesn't have to encode them as pairs. It can every time encode which one it wanted to do, and we put in one branch in the decompressor to make that happen, right? Now, as you can see, that means that essentially we've got two loops here, and these loops are almost identical, right? They're almost exactly the same. You can see them here, right? We've got while count minus minus, while count minus minus, and the only difference is which thing we're taking from. So what I might further say, just to keep this decompressor, just to hammer home the point that the decompressors are so simple, a lot of the times, if we were to just say, all right, what if we just made our source be dependent, just the pointer dependent on which one we were going to do here, right? And then we could maybe avoid having to do, we could just have a single loop, right? Just one loop that executes. We don't have to have two different loops, right? And it's not quite as pretty as we might want it to be, right? And these are actually backwards here. There we go. So, if the copy distance is 0, then we copy from in. If the copy distance is not, then we do sort of our replication. But the only problem that we get here is that we don't know actually which of the, once we do this, we've pulled the in pointer out into the source pointer, which means that it won't actually advance, right? And we need it to advance by the count in the case where, we were going to actually, copy from in, we need in to advance. So really, we need there to be something like that where we move it forwards. And I'm not sure there's any really cleaner way to write that, right? So I can't quite see how to do. I guess you could just do this. Right? Yeah, but I don't know that there's any way to do it any more cleanly than that, unfortunately. You don't really want to execute the if in line, but you can kind of see that it's relatively straightforward, right? So yeah, is there something, am I missing anything cleaner we could do there? I don't know. Really what you want to do is just have it be like, there and have this happen after the fact. That would be the nicest way to do it, but unfortunately there is no sort of post-decrement with a variable size in C, so I think that's pretty much the only way you could do it, if that makes sense. So yeah, so maybe, it's better to just say like, okay, we've got our source pointer, and we just say, if the copy distance is 0, then the source equals in, and in plus equals count. And I guess I could just sort of do that. So again, not quite as concise as I would like, but still very, very small, right? Very, very simple. And so we come in here and we say, all right, well, we have stuff to ingest. We grab the count that we're going to use out of the current location in our input stream. We grab a distance as well. And then we look and say, OK, when we see the distance, we will say, if it is equal to 0, then we're going to copy from the input, and we're going to advance the input by however many things we're going to copy out of it. Otherwise, we're going to look backwards the copy distance from our current output location. Then we're going to use a while loop to go for as long as we were told to go, copying from whichever one of those we decided to copy from. Right? And so there you go. That's about it. Now, you'll note that in doing so, when I said we were going to use that extra value, we give something up in terms of compression for doing that. Because previously, when the encoder didn't have a decision and it was always done in pairs, doing it in pairs has the advantage of not needing to encode the fact that you were going to do one or the other. So what we did is we gave up a byte here. Every time we want to encode a series of literals, we will have to encode a byte. And that byte, there's a 0 byte basically that would have to be encoded there. And that might be a bad decision, right? So it may be that it would be better for us to do, depending on what our circumstances are, it may be that it would be better for us to always do in pairs where we go literal, repeat, literal, repeat, literal, repeat, right? Like we were doing in RLE. It might be better for us to go like literal, copy, literal, copy, literal, copy. If the data tends to be of the format that allows us to do that interleave, then that would always be better, because we're saving 1 0 byte every time we do that interleave. However, if most of the time we aren't doing the interleave, if most of the time we're either we're doing like unusual, like unpredictable patterns, like copy, copy, literal, literal, copy, 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 literal, whatever, then we've saved quite a bit. So it's really hard to say, and like this is sort of the way compression works, right? You're constantly thinking about all these sorts of things, and if you were a compression expert, which, as I've said many times, I am not, you probably have strong opinions about a lot of these things, and to the nth degree, right? Like much more complicated sorts of stuff than what we're talking about here, but they all follow that same pattern of, well, if I encode something this way, then I get some benefit this way, but I lose something here. Is that the trade-off that's appropriate for the type of data that I'm doing, blah, 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 right? So that's that. So let's go ahead and take a look at how to do the compressor now, as opposed to the decompressor. So here is our RLE compressor, and we'll just kind of grab that and start with it, like we did with the decompressor, because like I said, they're basically the same, but more. Is compressor that way or that way? I don't even know. Doesn't matter. Anyway, point being, so if we have LZ compress, we're going to do basically the same thing we were doing before. Let's start by just making something which doesn't actually ever encode any real dictionary lookbacks. We'll just do something that encodes RLE, essentially, but inside LZ, just like I said we could do, where we're just using LZ's ability to do RLE inside it in order to compress. Right? All right. So here's our LZ compressor. I feel like I have something stuck in my teeth. I know that has nothing to do with... I know nobody cares about that besides me, but I just feel like I do. Anyway. So if we take a look at the LZ compressor, starting from an RLE compressor, you can kind of see that we would have to make a little bit of changes here because we're giving our LZ compressor the ability to decide which one of the two things it was doing. And if you recall, inside our RLE decompressor, the reason that we didn't really do it that way is because we didn't super have any way to encode that, right? We could have, there wasn't anything sort of for free in one of our things that we might have wanted to use. All of these values are sort of maximally used. Now, we could have just used a value that was reserved in here where we basically said, like, okay, if we do a rep count of 0, right, then that means it's literals coming after it. And so the rep value would actually be how many there are. Whereas if there's a rep count of, you know, a different number, let's say, then we know that it's a copy. So we could have done that as well in the RLE, sort of. But it's not as obvious as in this one where it's like, oh, hey, there's going to be a thing that's got to be 0, that has a big old 0 hole in it. You're going to have to adjust for it one way or the other there. But anyway. So yeah, so it's unclear. I'm not really sure. Maybe that was a stupid thing to do, but well, I don't know. We'll see. So here's our LZ compressor. We come through here, and we're starting to ingest the data, right? And we're going to use a literal buffer just like we did before, which is just whenever we see something that we don't think we want to encode, we're going to shove it in there, and then we know that eventually we have to kind of flush that buffer as the case may be. So what we have here is our run length encoder, right? It's a part which is basically looking to see whether we've got a run of something. And so let's use exactly the same logic, right? Like I said before, let's just encode runs with our LZ encoder. So what we'll do is say, okay, if there is a run to encode, then we'll basically say, like, you know, flush at this point. Otherwise, we buffer. So the first thing we have to do is see, are there any literals to flush, right? So we take our literal count 8, and we say, are there any literals in the buffer? Because remember, unlike the RLE scheme, we've given ourselves a way where if we don't have any literals to encode yet, we don't have to, right? So that's kind of nice. So we say, OK, are there any literals to encode? If there are, flush the literal buffer, right? Out it goes. And so the question is now, well, how do we encode that? Well, remember, we can look at our decoder for that information. We do a count and a copy distance. The rule is if the copy distance is 0, then it will copy from the input. So all we have to do here is say, all right, we're going to output two things, the literal count, which is the count that we actually wanted, and then a 0. And that tells it, OK, we're going to literals are coming next, and here they come, right? There's our literal count reset. So we're good to go. And then we come through here. Now we've got our run. We want to output our run. And the way that we want to output the run is we want to say, like, hey, output a copy of the thing that came before us in the buffer. Now, it's a little bit complicated here because effectively we have to sort of put, how should I phrase this? We have to have outputted the thing that we are going to be running with, if that makes any sense, before we can replicate it. So technically, we're going to have to modify this routine to be looking for matches that start with the previous symbol, but we can do that in a second. It's not too difficult, right? But anyway, so let's assume that we're talking about a run that starts with the previous symbol. In that case, we just have to output exactly the same thing here, right, that we were doing before. But now, instead of outputting a 0, we're going to output that run, the run length, right? Or I should say the look back length, and the look back length is going to be 1, right? So instead of outputting a starting value, we're just going to output a 1 here, which is say look back at the previous symbol and replicate that for whatever the run size is. OK. So in this case, what we're going to do is say, all right, there's a starting value here, and that starting value is going to be something from the from the previous, right? So the starting value is going to be something from the previous character, and we want the run to start at 0 now, right? Because we're going to look at the initial character and say, okay, is that a run from the previous character? So when we look at the starting value, this is actually going to be the previous. Now we can't look at the previous if we're on the very first one, right? So we have to do a thing where we're going to be a little bit more careful about when we actually start doing this thing, right? So if we start off with the run at 0, we need to now check, is in greater than the starting in, right? And so we just need to make sure that we've gotten somewhere first, right? And that's about it. So when we actually have to go, so this for buffering literals here, I think this is probably just better written like that anyway. So I think that's really all we need to do. And so now we should be able to run this, and we'll have to kind of step through it because these things are kind of delicate, obviously, so I can't promise that I dotted my I's and crossed my T's there. But now we've sort of got the ability to run this guy as just an RLE compressor, which is, again, not going to be very good. In fact, it's probably going to be worse than our other one because it's basically got a bunch of stuff it's baked in there for it to do that it doesn't need to do, or that it's not using, rather. But we'll get to that eventually. All right, so let me load up MS-Dev here. And let's step into the... OK. Forgot we need to call it. There we go. And so let's go ahead and jump in now. And why are we... Oh, we're on the decompressor. That's no good. I don't want to be on the decompressor at all. You know what else we should probably do, actually, now that I think about it? It might be nice to just have a test. If we're going to do test, I was thinking like, oh, okay, what if we just do something where we go like, okay, you call test, and it goes, give me the data, let's make an output buffer, and a test buffer. The test buffer will just be a buffer the same size as whatever the input is. Right? We'll go ahead and say, okay, compress the thing. So here's the compression, right? And then decompress the thing. And that'll run the compressor, then the decompressor. And then we could even do a memcomp, which I don't think we've ever done, because we don't normally program using the standard library on Handmade Hero, right? We almost always just write everything ourselves. But you can kind of see here we've got the ability to use the C standard library. A memcomp is just a thing that says, hey, compare two pieces of memory and return to me a difference between them. So if there's no difference between them, it'll just return 0. If there is, it'll return non-zero, right? So what we want to do is say, like, if memcomp, and we want to pass that file size there, we just want to say, hey, if our input buffer and our output buffer match, then we would just say, like, okay, maybe just say success. Otherwise, we just say failure. Right? And so now we can just have a single way to run it when we're doing development that would just allow us to figure out what's going on there. And so in this case, we've got test1.hha. And we can just do test1.sp, but the second parameter would actually just be ignored, I guess, in this case, because we're not going to actually write it out. Now, I suppose we could actually write it out so that we can run the test and have the output saved, which does seem potentially useful, but nah, I'm not going to bother. So really, I suppose that's something better done in an arg count equals 3 scenario, but whatever. Don't really care at this point. All right, so let's go ahead and run this. So I can actually get to my compressor now, which is what I wanted. So here we go. So the first time through the loop, we can't actually have a run because, again, we can't look backwards to see if we've encoded something that we want to replicate. So we're going to skip these the first time through, and we're just going to buffer a literal, and there it is, right? The next time through, we're going to look to see whether or not we have a run from the previous. And in this case, we do, because the h is duplicated, right? So now the run, of course, would have kicked in, but it's not long enough, right? Because it was only one replication from what we had output in the literal, which isn't good enough, right? Now notice, again, that's a difference from the RLE, because like I said, the LZ can only RLE something it's already output, right? Which is, not as good, right? So anyway, so off we go, and then we're just looking. Here we found a much longer run, a run of 3. And so now we're going to actually encode one of these runs. Here is our output, our literal count, right? Is getting output then to 0, and then we're outputting literals because we do need to flush the literal buffer, right? The literal buffer is now flushed, and now we're going to say, okay, now we're going to run that last saucy fellow for 3 times. So here we go, and then we're going to go forward by that amount, right? So I think we're good now. I think that will do our encoding for us. Don't quote me on that. But here we are on the decompressor after having done that. And let's see what we get. So we read in count first, and the count is 5. And the copy distance should be 0 because this is a literal. So let's take a look at what we're going to copy. Here's the thing that we're going to copy, which is, there it is. HHAF, and then some noise, which is exactly what we want. So we output that literal, right? There it is. Now we come back through and we learn, okay, we're going to do a count 3, and we're going to do a replication from just the previous thing, whatever that was. So there's our source, right? And it's going to copy a 0 a couple times. So there it is, copying a 0 a couple times. And off we go, right? And it just keeps going. Now it turns out that unless I wrote the comparison wrong here, we should be able to determine whether we succeeded. It looks like we did. So hey, we wrote our compressor right the first time. So that's great. And let's see, just for our own amusement here, let's go ahead and see how well we did, right? There's our test1.hha. We'll start with that one. So if I want to do simple compressor, compress, test1.hha, test1. Simple LZ or something like this, or I guess we'll say run length RLZ, run length LZ. Let's see how that does. So you can see that actually, amusingly enough, we're still smaller, even though we haven't actually implemented the LZ yet, because the test1.sep, the RLE one that we were doing before, in fact, I could. Probably the fact that it had to do alternating pairs of literals and runs was probably causing it to be not as good as it could have been, right? Because now that we've gone to the LZ, we haven't actually implemented LZ yet. We're already smaller. It's probably because it can take advantage of that, right? Furthermore, I can go ahead and say, like, okay, introart.scp here is introart.rle. And then I can do simple compressor, compress, introart.hha, introart.rlz, and that'll do the compression on that big huge file, and then we can see how well that one does. And again, this one is not really doing LZ at all. You can see this one doesn't do better, right? In this case, the RLE by itself is actually an improvement. I guess because, again, presumably that alternation happens to fit the pattern okay, so it doesn't lose anything, and it doesn't have to encode that 0 every time, so, who knows. But that's just conjecture. We haven't actually looked at it yet, right, so we don't really know. But that's just interesting to take a baseline of, right? All right. So now let's actually try to implement actual LZ compression, because like I said, this is not LZ compression. What this is is strictly us using an LZ backend to implement RLE, which is not what we wanted to do. I just wanted to sort of demonstrate that that worked. What I want to do now is extend it so that not only can it do runs like that, but it can also actually do lookbacks at, which is what it's supposed to do, right? The whole point of dictionary compressor is to use a whole bunch of stuff in the output stream from anywhere, not just the most recently output thing, which is what the only thing we're doing now. So in order to do this, I need some way of looking back over the stream to see where in the stream we would get the longest match from. Now, the first thing I'm going to do is implement something which is incredibly, unbearably slow, probably, and we would not be able to run. Well, actually, you know what? I take that back. The first thing I'm going to implement is a very slow way of doing it, but because we're only talking about bytes here, and the look-back buffer is only 255 bytes back, this probably won't be prohibitively slow, because computers are so fast nowadays, they can scan a 255 window really easily. So, you know, take this with a grain of salt. Because 255 to 255 is only 65536, that's extreme, or 65534. That's a very small number of iterations for something to do on a modern computer. So surprisingly, this will probably actually run just fine. But if we were to upgrade that look-back window to more like 16 bits, which is a more common size to use, and there's a number of reasons we can talk about at the end of the stream if someone wants to remind me about why 255 is not a particularly good look-back number for graphics compression. I can talk about that because it really isn't. But we'll go ahead with this for now, and you can see. So first, I'm going to implement the stupidest possible thing. So how would we look for a run where we could say, let's look back over everything in the buffer that we could possibly access and just see what the longest match is, right? Well, if you think about what that would look like, we could just say, well, okay, let's say we just start as far back as we can. And so we could say, like, all right, start of window or something. Well, that's wherever we are at the moment, minus whatever our max run count is going to be, right? And I guess we shouldn't say max run count. We kind of need a new thing here, which is like, max look back count. And we'll just keep that in there. So we've got our max look back count, and we're just going to say, like, okay, whatever the maximum value is that we could look backwards, let's start with that. Now, the start of the window here may be behind the beginning of the buffer, so we also need to double check, right? And we need to say that, well, if we haven't gone that far yet, we can only go as far back as we have actual data. So really what we're talking about here is more like, okay, max look back equals, whatever the in pointer is minus the in base, right? So that's how far we've gone. If the max look back is greater than this value, then we use it, right? So we're sort of like only using to the beginning of the buffer, but as we move forwards, we may then start pulling that window with us as we get past the 255th byte of the buffer. All right. So now we want to go ahead and I guess we'll just do it like this. Here's our window. We know that wherever we are, we're going to go back however much that look back is, right? And then we're going to step all the way up to where we currently are in the stream, looking at each individual byte, right? Maybe we'll call this the window base, right? Or maybe window start. Right? And then what we need to do is we need to do something almost exactly equivalent to what we just did, which is to say when we encode when we are looking for a match, we can only go as far as the maximum run count that we could have encoded, right? Because as we're looking for matches, we can't look for any matches that are longer than we can encode. We can only encode matches 255 long. So even if there was like 1,000 zeros, in a run of zeros or something like this, we couldn't, encode more than that, or any pattern. I mean, it doesn't have to be constant anymore because this is LZ, not RLE. We could, it could be any pattern. Any replicated pattern can only be that long. So we need to do exactly the same thing. We need to say, well, the end of this thing, right, is in end, right? But we don't know that we can actually go there. Right? So essentially we have a window size, and the window size is going to be however long we have till the end of the buffer, but if that is longer, which most of the time it will be, if that is longer than the max run count, then we can only use the max run count, right? So the window end is going to be oops, I messed that up. It's the window start. There we go. So from where we're looking to the end, that's how big the window can be, and the window end is going to be wherever we started plus whatever that size is. So now we know where we're looking in this particular window. So now we just need to see how big of a run we can make with that matching from there, right? So what we want to look at is we want to look at the test in versus the window in, right? So the test in is where we're at right now. The window in is whatever the window start is. And then we're just going to go ahead and say, you know, while they're equal, right, we're going to increment them. And in fact, we could just do it this way. So we will count the run just like we were doing before. So we're going to look in the window and say, okay, how far can we go? While we're moving, off we go. But we want to make sure that we never exceed the end of the window, right? So we want to say, okay, cap the window in to the window end, right? But as long as we're doing that, test to see if the two things are equal. The input stream and the window, you know, are they the same? And if they are, keep track of how many of those we could do. So after we pop out of this loop, we will now know the maximum match we could do at this location. So then we just have to do our standard thing you've seen on Handmade Hero many times, is keep the best one of these, whatever it is, right? So if our best run size is less than our test run size, then what we want to do is our best run becomes our test run, and our best location equals whatever our test location was, right? And I guess all we really need to know is what the look back was here. So actually, it's just however far back the window start is. So we just want to kind of know, like, oh, okay, how far back do we go to get to the window start, right? So I don't know what best distance, I guess we'll call this. So then all we need to do is actually keep those, right? Best run, best distance. And so then when we come through here, we don't care about this anymore, right? This is not, we're not doing that anymore because we're finding the run a different way. And then when we come in here, we've got our best run. And now we're going to do exactly the same things that we did before, right? OK. So cleaning this up, we now know that out of this, and we'll have to step through this and be careful and make sure we did everything right, but coming out of this is assuming that we have our best run and our best distance. We now, though, we can say, OK, when do we want to encode a run? Well, we know that a run is going to cost us something, right? And it's going to be a little bit interesting to look at the cost here. But so I'm just going to put a little to-do here because we'll do it in a second. Think about when to output. But for right now, we're just going to use if the best run, if there was any run at all, right? So if the run is greater than 1, we'll use it, right? So then we come in and we need to do our flush. We need to do our literal count flushing. Now, one thing that you'll notice that I forgot to do when we kind of added this in just moments ago is really if the literal count was the thing, if the max literal count was hit, then we don't actually need to encode the run, right? Because if there was no run to encode, you know, if the best run was not sort of something we need to encode, then we don't actually need to do any of this, right? If that makes sense. So if the only reason that we went through here is because we needed to flush the literal buffer, right? Then that was all we need to do, right? That's all we need to do. And then we just want to restart queuing literals up at the beginning again, right? So I believe really what we want to do is sort of have something more like this. Output run. And I guess we don't probably have a bool here. There we go. Right? And then in this case, We're now using best run, and off we go. Okay, so I guess this is probably a size t here. That's supposed to be window size. Okay. And now what we need to do is just say, all right, now remember, we're no longer trying to encode just copies. And so we've got this distance value that we actually need to use as well. And so now, right here, we need to actually do our distance 8 equals u8 best distance. And we want to assert that that distance 8 equals our best distance so that we know that we didn't accidentally overflow. And then we just output that distance, right? And that's it. So now we've effectively got something that will actually look back over the entire window, find the longest run it could possibly output, and output that run, right? And now that's, of course, assuming that we didn't mess it up, which we may well have. Now, according to our test, we passed, so I guess we wrote the compressor at least in a way that doesn't crash. But we have no idea if we actually are compressing particularly well or anything like that. But we can certainly try it now. So let's take a look at again, doing our simple decompressor, sorry, simple compressor. To do an actual RLZ, here's our simple LZ. And now it's going to do its compression. Here it is. And so taking a look at the simple LZ, we have not done a particularly good job, it looks like, actually. So that's actually bigger than our strictly our run length one, which perhaps is not surprising. Now, why is it not surprising? Again, we could have a bug in here, so we're going to have to step through. But at least I'm going to finish this part before we actually step through and see if we're working properly. Specifically, if you think about what this is doing, now that we're looking back over the window, it's highly likely that we will often find pairs of bytes we can replicate. And the only thing that we're checking for here is whether or not there's a pair, right? It only has to be 2 before it will do this. But what that would mean is if it was going to have to do an output of 2, it will have to write 2 bytes to flush the literal buffer, then any literals that it has, which of course we don't count again. So it's 2 bytes there, then another 2 bytes here to do the run. So it's actually expanding every 2-byte run into 4 bytes for no reason, right? So given that, excuse me, what we want to do is something more like this, right? What we want to do is say, all right, first of all, are there any literals in the literal buffer, right? Because if there are literals in the literal buffer, it means that in order to output a run, we're already going to have to flush the literal buffer, which costs us 2 bytes, right? We're going to have to output this, and then the literals. So if we're already doing that, we had better make sure that just adding the literals that we have onto the end of the literal buffer isn't a more efficient approach, right? So in this case, what we want to do is say, all right, the run that you're going to have here had better be greater than like 4 bytes. Because if the run isn't greater than 4 bytes, it's going to cost us more to output it than it would otherwise, right? On the other hand, if we don't have to flush the literal buffer, right, then technically we're only going to have to do 2 bytes to encode whatever this duplication is. So technically it only has to be that good before it's better, right? Now when I say better, I mean in a very like loose sense here. And we'll talk about that in a second, right? Or at least hopefully I'll remember to. Okay. So we'll just go ahead and put that in there, and let's do these two. And so let's see if that improved it at all. Now again, we haven't stepped through it yet. Excuse me. So I'm not sure if we're actually properly working yet. So that makes it a little bit different. But you can already see that, you know, if assuming we are working, you can see that with that change, we are now down to a much smaller file size, right? Compared to where we were. We were worse than the other two before. Now we're better, right? And so that's pretty handy, right? So it's like now we can see, oh, okay. Before we were, you know, 175. Now we're down to 158. So we're the best compressor of the three now. Before we were the worst. Okay. Now again, like I said, this is very, very slow because we're doing that search, which is very expensive, and we're not accelerating it at all. So the downside to this is if we want to run one of these guys, well, it's going to take a while. Here's our intro art. Let's go ahead and run that, and we're going to be running it for a while, right? It's got to kind of sit there, and it's going to like churn and churn and churn and churn and churn and churn and churn, right? Now, we can fix this a little bit. If we open our build, we can at least get some O2 on that, right? We can at least have the compiler optimize it for us, which I believe it's going to do, right? Because we've passed the flags to it, do we not? Yeah. We passed common compiler flags, and the common compiler flags should have that in there, yeah. So if we do this, we should get a little bit of extra speed, but of course it's still going to be very slow because it's just fundamentally doing all that search. And so, you know, we'll just let that run. I'm going to get a drink while we do that because I am parched. Hold on one second. All right. So, all right. While our little, completely n-squared compressor is chewing through this ridiculously large file, we can go over here and play with our notepad. All right, so let's talk a little bit about optimal parse. Basically, the problem that we have here, and you just saw me do a little bit of it, is that LZ schemes have a lot of decisions. Right? And this is what I was talking about before when I said, like, oh, the compressors get more complicated because it's essentially an AI problem. It's got to do a bunch of intelligence here and graph searches and optimization of sort of thinking-based optimization in order to figure out what the best way to do something is. It's definitely a maximization kind of process. And so what do I mean here? Well, as you saw, where is it? Let's go to some compressor. Here you go. As you see here where we've got, literal count, and I don't know why I'm on that side. There we go. As you see here, I've got, this if the literal count, then output the run if it's better than this, or output better than that, or whatever. We already, even though we're not doing anything intelligent, we already have this concept of trying to weight two different options based on which one we think is going to be better for compression. But is this the whole picture? No, it's definitely not the whole picture. Why? Because every time we encode something, we affect the decision-making process all the way down the line, right? And so if you think about what happens, let's suppose that we have something like, A, B, C, D, E, F, G, H in the buffer or something like this, right? This is what we've outputted at this point. And we're talking about what to output next, let's say, right? Well, I guess I maybe need one other thing here. Maybe I want something that looks like... This is not going to be a very good example. I'm trying to think of exactly how I want to output this. So let's say that I've got this in the buffer, and then I have another thing in the buffer, which comes from part of this. So let's say it's I'm not sure. My compression non-expertness means it's hard for me to come up with a case on the spot that demonstrates what I mean about picking the wrong match. Because we can pick matches from anywhere in the input stream, but we don't necessarily always know which one is going to be best. So all right, here's one that, okay, here you go. So let's suppose that we had something that was like, very interleavy. So it was A, B, C, D, E, F, G, H, right? And then we had something that was like, trying to encode something. And then we had another one here that was like maybe 1, 2, let's say, A, B, and then we had another like, okay. So this is probably going to be a really bad example. Again, this is because I don't do compression hardly ever. So, I feel like if you were a kind of person who did compression all the time, you would be able to think of these examples much more cleanly. But, so imagine that we're trying to output things right here, okay? Well, if I look back in the stream and I look at for the longest match right here, you can see that the longest match is this one, right? 1, 2, AB. Which is just long enough that we would probably choose to encode it, which would put us right here. And then we would look back and we would find that the longest match was like right here, right? It's C, D, E, F, H, and it goes that far, right? Well, probably, if this was a literal, it probably would have made a lot more sense to just include these two in the literal, right? And make this literal slightly longer, then include this very long match. Because that would allow us to only send an additional 2 bytes of data to encode this match, rather than having to encode 2 matches, this one and this one, which would be 2 extra bytes each, right? So every time you make a decision, you're making a decision that affects all the future decisions that you're going to make, because you've changed where the outputs, where you're going to be making your decision points, right? And so the concept of an optimal parse is basically the concept that when you're doing one of these compression passes, there is some set, there may be more than one, but there is some set of ways of choosing where you broke up the stream like that will produce the smallest possible output size. And lots of other decision sets you could make will not produce the smallest possible output size, even for the same encoder, right? And so that is what this sort of thing is about. Typically, you are making a bunch of pieces of code that operate inside your compressor that are much more complicated than this, whose goal is to figure out whether or not you should encode matches, encode literals, etc., based on heuristics, right? Now, you could try to do the actual optimal parse, because, for example, you could just try everything. Try every possible way of breaking up the stream. But again, it becomes prohibitively expensive to actually run those things. So you have to use, dynamic programming or something like this to make it a little more tractable, and then maybe you don't test everything, you just test some things. And you can imagine it just getting much more complicated as you try to make something which actually does look across all of those options. Now that I'm done with the explanation, you can see that we've got our output here. And let's take a look at how it did. So here's our simple LZ compressor, and you can actually see it's real good compared to our other two compressors, right? It's not quite down in the range of a really good compressor like 7-zip, but that's pretty great. I mean, we've this is less than half the size of our art pack, right? That means, if it was going to take 10 minutes to download before, it's going to take 5 minutes to download or less now. That's pretty great for a really stupid compressor, right? But hey, it took a long time to do the compression. So the next thing you might want to do is start looking at how you would speed it up, right? So we don't really need to belabor these points right now, but I'm going to go ahead and put a thing in here. So let's talk a little bit about what you might do with this compression code to start to make it better. One, figure out an efficient way to expand the LZ encoding to support, greater than 255 size look back and or runs. To add an entropy backend, like Huffman, arithmetic, ANS, right? So adding an entropy backend would be another great thing to do to this code. Add hash lookup or other acceleration structure to the LZ encoder. So that it isn't unusably slow. For add better heuristics to the LZ compressor to get closer to an optimal parse. 5, add preconditioners to test whether something better can be done for bitmaps, like differencing, deinterleaving by 4, etc. So there's lots of things that you could do, and compression, certainly you want to learn more about compression if you were actually going to try and do something good with compression. That's better than what we're doing here. But the other aspect of compression that generally tends to be true is even after you really know what you're doing, there's just a lot of, for lack of a better term, fiddling and refinement. Getting to a reasonable state theoretically is one part of the battle, and that's obviously good, but then just the actual mechanics of how you get things to be encoded cleanly and how you work out all of the details and make them fit the problems that you have as well as possible, those things are definitely, those are a whole different set of techniques, which is a lot more like optimizing render code. There's just a lot of iterations and testing and measurement that's necessary to do that, right? So yeah, I think that's basically it for that. I'm going to go ahead and add just a little bit more, I think, to this framework here, just so we can maybe maybe if anyone wants to play with it and do some stuff, they'll be in a slightly better position. So what I'm going to do here is just say okay, maybe there's some kind of a way that we expose statistics out of this, and I'm trying to think about how I would want to do that. Let's suppose we did something like maybe an enum here, which is like stat type. And then we would have something like, you know, or I don't know what you want to call it. I feel like you need a different name for like a repeat versus a copy back. I don't know. We'll call it that way. We'll call it something like that. Stat literal bytes. I don't know. Let's say we've got a bunch of stat types here, right? And I want to print these things out. And then I'm going to have a struct like stat and a struct stat group. And then I've got my stats here, which is however many there are. And then my stat is just going to be a count and a total, something like that. So basically what I want to do here is just create a little thing that allows me to record information about, you know, what's going on. And maybe I've got, in addition here, I've just got like uncompressed bytes and compressed bytes. Yeah, so, well, actually, I suppose those are things that we actually just kind of know. So maybe that's not in the stat group. Maybe that's down here. Just trying to figure out a good way to keep track of all this stuff. So we've got, yeah, we've got all of our stats that we might want to output. We've got the stat group here, and off we go. So what I'm going to do is I'm basically just making a little thing that will make this a little bit easier to use for various purposes. I'm going to take here and make a compress and an uncompress kind of thing into a type def. So I'm just going to pound define like compress handler and decompress handler. So here they are. So I've got the compressors. They'll all look like this. I've got the decompressors. They'll all look like this. And then we'll just do type def compress handler. Type def decompress handler. All right. There we go. And so now what I can do is I can just sort of make these, and we need to actually figure out something here for a reasonable size, you know, kind of some kind of thing that handles the size more reasonably here. But let's go ahead and just say we got compress handler, RLE compress. Decompress handler, RLE decompress. Compress handler, LZ compress, and decompress handler, LZ decompress. So at that point, once we've got those sort of handlers there, then I can sort of also define this idea of like a compressor. And the compressor can have a compress handler and a decompress handler. And you'll notice I want to have both kinds here. I want to have a compress handler and a decompress handler pointers, because we may want to use the same decompress handler for a whole bunch of different compressors, because we might want to have different compressors that we try or whatever. Some, who knows. And so what I can do is I can say we've got compressors. And these are just going to be like compress and decompress pairs for like all the stuff that we've got, right? So you can imagine like we just say like, oh, okay, we've got a bunch of compressors. We've got the RLE one, right? We've got the LZ one, and maybe we want to do a thing in here where we're going to name them. Who knows? Okay. So let's assume that that's how we're going to do it, and maybe get rid of these guys, and then when we go up to our compressor here, we'll just say like, oh yeah, okay. So the compressor has a name, and this way we can say like, when you are specifying something here, when you do the arguments or whatever. We can say that when you do compress or decompress, before that, maybe this becomes a 5, and we do a little check to see which compressor we're talking about, right? Yeah, I mean, I guess the other way we could do it might be to say, as long as it's greater than 4, we take all of the ones and we use the compressor for each one or something. I'm not sure. We got to think this through a little bit. I don't know. We'll do the simpler one first and just see how that goes. But point being, we should be able to say something like, okay, let's say you got to take 5 arguments, and so instead of 1, 2, 3, we'll do 2, 3, 4, and we'll say here char compress or codec name. And that'll be the first one. So the first thing we'll do is try to find the compressor. So we'll say compressor equals 0. And we'll just go through all of our compressors. Compressor index equals 0. Compressor index is less than, however many there are in that array. Right? And then we'll say, OK, compressor index and we'll just check the string compare. So if the codec name and the compressor name are the same, break out, and that's that. So this is really probably should be right. So in this case, we only want to proceed if the compressor is known, like if we have that compressor. But assuming that we have it, then from then on out, we will just use whatever the compressor is that we found. So now, instead of calling compress, we're going to call compressor compress, right? Instead of calling decompress, we'll call compressor decompress, and so on. So hopefully that makes sense. Let's go ahead and rename these guys to be base so that they don't conflict, and then anyone who doesn't want that can obviously sort of play with that later. So this is going to be in base. Oops. And same here. And oops. And then I think we're good. So now, if we take a look at what's going on here, so let's do simple compressor, compress, and I think we wanted to say, like, let's say RLE, right, compress, test1.hha, test1 RLE out, or something like that. Let's see if that actually, oh, my goodness. Well, that didn't work particularly well. Let's take a look at what's going on there. All right, so in here we got now, let's put something on the front of this here. So I'm going to go ahead and step in. Compress, wait a minute. Also, we got to change the and we do not need this to be O2 anymore. We can go back to debug mode. There we go. So let's see here. What did I need to set the thing to? Arg count 5, 1, 2, 3. I forgot to put the compress in there. There we go. Let's step through here. There's the compressor. And we... oh. That's a nice typo there. There we go. All right, so let's see how that goes. So we go through here, we found our compressor, we go through, we compress with it, and we're done. Okay, so that's all good. All right, so now we should be able to use any of the compressors that we want, which is nice. But we would like to maybe do a little bit more here in terms of outputting some statistics and stuff, like I was saying before. And we also might want to output the algorithms that you can use as well. So, you know, we could go ahead and put that in here, where we say, like, okay, you know, algorithm not a particularly good help system, let's be honest. But there's like what the algorithms could be, right, at the moment. And off you go. So now the only other thing, like I said, that I want to do was have a concept that stats come in to play at some point. So what I'm going to do here is I'm going to say that, hey, we're going to pass stats to both of these, so that basically, like, if they want to record stats, they can. And then what we're going to do here is say, like, okay, there's, you know, sort of a stat that comes in uninitialized that we pass to the compressor. I guess decompressor maybe doesn't need stats now that I think about it, because we don't really care about recording stats for the decompressor. So probably we're only really talking about stats in this case, where we're calling the compressor. All right. So yeah, so now we're passing those stats through. And now really all I want to do is have a way to dump the stats out, right? So I want to be able to take these stats here and output them, right? So it's kind of annoying. This is one of those C things that just really is awful about C and C++. I just want to be able to get the names of these things so I can output them. Of course, I can't. So that's kind of annoying. But, you know, I can make a function that does it. You know, stat name that takes stat type. And then just does this nonsense here, right? Well, I guess I could even just do, well, we'll do it this way. It's a little more robust than using an array because if you reorganize things, you don't end up with wrong printouts, which is kind of nice, right? So you can kind of see what I'm doing here. I'm just saying, hey, let's make a macro where we say if we're going to do this thing, we output whatever, you know, the thing is that we want. And we probably don't really need the stat underscore in front of it, so we could just say, like, you know, go forwards 5 characters and do that or something like this. You can imagine that being sort of an amusement that we could do. And of course, you know how much I hate const. It's the worst thing ever. So typically what I'll do is I'll just get rid of it. Right? I always get rid of const anywhere I possibly can. So now we've got a way to print out these stats. So you can imagine us going through, you know, something like this. I don't know why I made that an inline. So if I want to do, you know, a stat printout, and we've got a stat group here, then I can go through these in a pretty straightforward way, right? And again, I don't know why I'm on that side where my head gets in the way. So let's go over here. So if I have one of these stat groups, I can just kind of come through here and say, all right, what's my stat index? Go through them all, like so. I want to grab out one of these stats, so I just say, all right, let's take each one in turn. If anyone recorded anything to the statistic, we will print it out. Otherwise, we won't. I don't know if we want to print these to standard error, standard out. Maybe standard out. I'm not sure. It's a good question. I'm not sure which is the more appropriate. But we're like, OK, this particular stat, right, and it's going to be, I don't actually know how to print out, with the C runtime library, how to print out 64-bit things reliably. It changes all the time. So what I'm probably going to do is just print them out as doubles and say that I don't want any additional number to it, right? Because that'll allow me to make sure that it's, you know, that it's properly printed out on any particular platform you might be on without having to guess what that platform is going to do in terms of asking to print out a 64-bit variable. So yeah. So, you know, oops, I should probably put that up here first. So uncompressed, or like, maybe we'll do like compression first. It went from here to here, and then, you know, we've got a particular percentage. So what I want to do here is say, like, all right, we've got a certain uncompressed size and then a certain compressed size, and yeah, I could say if stats uncompressed bytes greater than 0. Then we go through and print them out. So we get our compression goes from whatever our uncompressed bytes were to whatever our compressed bytes were, and there's a certain percentage there. I'm going to introduce a function just called percent, where I can pass two things that I want the percentage of. And so usually the way compression percentages are phrased is what percentage of the original file size the output file size was, I believe. So it's like the compressed over the uncompressed is, I believe, how they typically are stated. Again, not a compression person, so I don't really want to suggest that that's for sure, but I believe that's how it is. So we'll do a numerator and a denominator here on this. And so what we want to do is we want to say, like, if the denominator is not 0, because we can't do a divide if it is 0, then what we're going to do is return an actual valid result. Otherwise, we'll return 0. So in this case, we'll say numerator over denominator, off we go. We are actually, where are we on the timeline? I don't even know. We're probably just about done, but either way. Okay, let's see. I actually wanted that to be that way. There we go. Okay, so that gives us a way to start printing out our stats. Now, for each of these stats, whatever the stats are here, we don't really have a whole lot in the way of sort of ways of looking at this data necessarily. But so for the first thing I'm going to do, I'm just going to print out what they are, and then we'll start to think about what we want to actually output. In fact, what I should probably do is say, okay, out of the total, certain ones of these out of the totals of what they were, we would want to sort of have internal summing, right? And I guess we don't really have a good way of outputting that stuff, so we'll sort of start with something basic, and then we'll see maybe if people wanted to improve the stat system, they could do that as well. All right, so inside print stats, let's just do the basic thing, which is to say, for every stat, we'll just output what it actually is. So here's our stat count, and here's our stat total. And then all I really want to do here is introduce, and these can kind of come down now. All I really want to do here is introduce an idea of, an increment for the stat. So, if we have a stat group, and we have a stat type, and then we have a value, then all that's going to do is say, hey, whatever our stat is that we're trying to increment here, we want to increment the count for that, and then add to the value. So this lets us know how many times we recorded something and then what we recorded, right? And so now that I think about it, that actually allows us to say literal, repeat, and copy are all actually we really need at the moment, because I think that's the only things that we actually care about there. So let's go ahead and do it that way. We'll just pretend that that's good. So let's go ahead and put our increment in here. So let's take a look at our compressor. For our compressor now, we can sort of say, like, okay, we can now actually record these things that we're talking about. So we could say increment stats, and then whatever our stat is that we want, and then whatever it is. So in this case, we've got a literal count, right? And we can say literal. We've got a run, right? Stat. Like so. And you know what? It occurs to me also that There is one thing in here that I think we're not doing quite right. I should point out that basically, like, we have to output a final, like, this will clip off the end. So we have to kind of input a thing here as well that's like, hey, if this is the last thing that we're going to do, like if in plus 1 equals in end, we have to flush, right? Meaning if in plus 1 equals in end, like if we're at the end of the buffer, so there's nothing left to do, we need to flush the literals out that we have, right? So we should put an assert here that like literal count is 0. Because otherwise we forgot a few bytes at the end of the file, right? And the same would be true of this one. So output run in this case, you know, in terms of the flushing and so on, is fine, but we need to do the same check. So here we need to say like, okay, if the next one is the end, there's nothing, if there's nothing else beyond it, then we would need to do it. And I guess, you know, now I think about it, that's not quite right either. In that case, we haven't necessarily pushed the literal into the buffer. So I guess really the way to look at it is more like if it's the last one, right? Like if we're on the very last one, then we need to flush. And we only check for runs in that case. So this is more like that, right? And I think that should all work because these should all be zeros, so it should be fine, I think. Famous last words, right? But I think that's fine. So we should be able to say, I'll go back and double check that in a second. We should be able to say while it's just less than or equal to, when we come through here, we can say like, okay, if we're on the last one, then go ahead and do it. And in this case, let's see, the window start is minus look back, in end minus window start. So it should be, yeah, I mean, I think all that should work just fine, I believe. But we should double check that, obviously. All right, so let's go ahead and clean this up here. Syntax error. What is the syntax error missing? Semicolon before, okay. Is that, there we go. All right, so I'm not quite sure we got all that in there yet, but let's just do one more here. Let's do a test of the RLE compressor first and see if that works. Retry, break. So in this case, I feel like, yeah, so run in this case, because it equals 1, will still increment the in pointer, which we don't want for our assertion. It doesn't actually cause a real problem. But yeah, so if you look through here, right, our running code needs to be slightly, a little bit smarter, right? So we want to actually start it like this, and actually make it do that copy from the initial one, if that makes sense, because that way, yeah, that way we won't actually get a run in that case. So when we output this run here, this would be an output of 0, I guess, for flushing the buffer. Yeah, I'm not sure. This is just a touchy thing to get right. Because there should be a more cleaner way, an easier way of sort of getting it flushable here. Because again, starting value is going to be an invalid value here if that's the case. So when it actually goes to output the run, which it always has to do if there was a literal, right? I'm not sure how we get that to work out right. Well, I guess it doesn't really matter because it's 0. So I suppose that's fine. The fact that it reads 1 off the end of the buffer isn't necessarily a bad thing. You know, but we could do this. Or something like that, right? Well, no, that wouldn't work either. Just kind of ugly is all. But handling that end, I'll have to see if maybe there's a better way to handle that end than that. Yeah. Okay. So let's take a look at this. So when we come through here, I kind of want to see... I guess it's a little bit hard for me to look at the case that I want. So what I might do is just put a little... There we go. So let's break here. So if we go in equals in end, then we know that we've actually hit the end of the buffer. So in this case, I want my starting value to be 0, which it is, so I don't read off the end. My run is also 0 because it's not going to go anywhere in here. And then I'm going to come through here and do my output, right? So I'm outputting a literal count of however much is left in the buffer. There are no literals in the buffer at the moment, so I guess it had been flushed previously. Which is a little odd. I'm not sure why specifically it would have been flushed necessarily. I guess because we ended with a run, which is handy. So we get the literal count. We take a look at the run count. We output it, and we output that final value. We then don't go forwards at all. Oh, right. We actually would have to break as well at the end of this, right? We have to actually stop on in equals end. So yeah, not great. I feel like we could probably code that more concisely. That's one of those things that tends to be harder, at least for me, to do on stream because I need to think it through, and it's hard to talk while you're necessarily doing that in terms of like fiddly things like that. But usually that does end up being the case. In this case, where we have a situation here, the same is true with the LZ encoder, where we're looking at these guys. We would also need to do a break to get out of the loop. So yeah. All right, so here's it doing the RLZ test. Let's take a look at what happens here. Looks like it succeeds okay, which means we get the same data out in both cases. So that's all good. And now let's actually call our print stats routine. So at the end of here, we just do our print stats. So now those will get outputted. What I want to do here is when we actually record the stats, I'd like to record the input size and the output size. So when we do like a compress here, I want to do like, stats uncompressed bytes, stats compressed bytes. Oops. Okay. And so, the uncompressed bytes is the in-file file size, right? And the compressed bytes is the compressed size in these two cases. And we won't look at the +4 for the size recording at the moment. We'll just leave that out of there. And we would do the same thing in here. And I think that's really all we need. That's a dot. So now when we call one of these, at least in theory, if we do a compress, we should be able to take a look at what's going on here. Okay, so clean up a couple things in our, where's our stats? Print stats. So yeah, one thing I forgot to do in our percentage is multiply by 100, right? Because typically percentages are printed out times 100. So we got to multiply by 100, and here, right, we forgot to print out the name, stat name, but then I think we're probably done. Sorry, get stat name, right? Get stat name. Index. All right. So in theory now we can actually get a little bit of visibility into what was going on. So you can kind of see for the RLE compressor, for the literals and repeats, you can see how many repeats it did versus how many literals it did. And hey, you know, the two are exactly the same in terms of how many. That's because the RLE compressor is an alternating one, right? So it has to do the same of each one. But the byte counts are very different. So it encoded 153K worth of literals, but it encoded 1.3 megs worth of repeating characters, right? And that's why we got such a good compression ratio here, right? Because most of the file consists of repeats. Let's try the LZ version and see what it says. Oh, well, of course I have to actually put in the stat counts there. So here's our LZ version. And when it comes through, when it does its flush here, we'll say, okay, here's the literal count. Here's the best run. Right? And what we could do is, in addition, we could say here, like, hey, you know, if the distance that we're doing is less than the run count, this is a copy, right? I'm sorry, then it's a repeat. Otherwise, it's a copy, right? Because that was like how we were doing RLE inside the LZ. So if the best distance in this case is greater than the best run, or equal to it, then it's a copy. But otherwise, it's a repeat. And it's a repeat of whatever that length is, right? So yeah, let's see what that will tell us. So here you go. So it looks like here's how many bytes we encoded as basically reps. Here's how many we encoded as like lookbacks, but that didn't rep. I assume I got this right. If the best is no, this is backwards. There we go. Right, because if it's greater, if the distance, oh wait, no, I did it right. If the distance is greater than the run size, then it is a copy, yeah. So there we go. That's a little surprising to me, actually, because I'm surprised that it encoded so many things as copies that were not reps, but that looks like the case. Am I sure I didn't get that wrong? The best distance, that's how far back we're going. If it's greater than or equal to the run, then yeah, then you wouldn't be repeating. So that would be a copy. That was surprising to me. I would not have expected that, but I guess that's the case. So for the sake of argument, or slight edification, I suppose, Let's also verify that we can do test here. There's our success, and let's see if the LZ passes as well, also. And we'll do our intro art.hha with the RLE, just to see, again, what those numbers are. And while we're running the old LZ, you can kind of see that's where, again, all the questions. While we're running our LZ on that, which obviously takes a while, let's go ahead and go to the Q&A. Let's see. Looks like there are no questions. That will make answering them easy. Miblo says, I think I followed it, but definitely want to rewatch during and after editing. All right. Forgive me if this information was somehow implicit in today's lecture and I missed it, but is compression ever used for locality wins? I guess I don't know what a locality win is, but yeah, I'm not sure. I'm sorry, I don't think I know what a locality win is in this case. I mean, I could guess, but I'm not sure I know what you're referring to. Do you know offhand what kind of compression ratio and decompression speed are needed before it's faster to load compressed data and decompress over loading decompressed data? The answer is it entirely depends on your backing store speed. So if the thing you're loading from is very slow, then you may get a win from any compression at all, right? Like if you're loading from a really bad hard drive, like, you know, maybe something like a PS4 hard drive that's really slow, old school 5200 RPM kind of style hard drive, then you may get a lot of win out of it, right? However, if you're talking about a really fast SSD or the upcoming X-Point stuff, those sorts of things, then you know, it's the compression is going to be a lot less effective, right? So it really depends on how slow, like how much compression you need for it to be a win in terms of I/O is really all about how fast the I/O is, right? Neil says int types and PRIU64 is probably what you're supposed to do for %LLU 64 printf. Yeah, but that is so variable. Like, it's which compiler are you on? Does it have a newer version of the CRT and all that stuff? So I just find like printing it out with float always works. So just do that, you know. The only time that you really can't is if you really are using all 64 bits of the 64-bit value, because then the float will lose a little bit of it, right? Because the double double's only 64-bit itself. Do you still have to uncompress your images for display? So do you have plans for using block compression? No, we don't have to worry about that because we're only using whole images at a time. So we only need to, I mean, I guess if you're saying, would we compress images individually, the answer is yes, because we want to load only the images we actually need. So that's definitely the case. But we don't need block compression like 8x8 block compression or anything like that, if that makes sense. Oh, Gary Johnson. I see what you're asking now. Okay. So the question from before is from, forgive me if this information was somehow implicit in today's lecture and I missed it, but is compression ever used for locality wins? And what he was talking about is he means like better usage of the cache. The answer is I don't think I have ever done that, but I suppose somebody probably has. Really hard to say. I mean, again, I'm sure there are cases when it could happen, right? I can't think of a time where I specifically had any experience with that myself. But yeah. Sorry, I do not know of a case offhand, but it certainly could happen. The problem is just that, you know, compression is kind of slow. Like even very, very fast decompressors are still not that fast. So, you know, the cache isn't that slow. Filling the cache isn't that slow. So it's tough, right? It's tough to beat memory speed with a decompressor in that way. And streaming is like the best case for filling the cache, right? Intel chips are really good at knowing that you're like reading a big chunk of memory in and outputting a chunk of memory. So you're actually going up against probably the best place, you know, in terms of, or I shouldn't say the best place, the case that it's best made to work with, because you can issue prefetches and stuff like that. So it's kind of hard to, yeah, it's tough. I would say it's probably tough. MTS Max, why is 255 not a good look-back limit for images? You want to elaborate on that? Yes, thank you for reminding me. The reason that I was saying that you probably want, for image compression, you want to expand beyond 255 is because most images are longer than 255 bytes per row. And oftentimes, you're going to copy stuff from a previous row to the next row if there's a duplicated, like, little bit of the image that might be similar. So if you can only look back 255, you probably can't get back to the same location on the row. Like to give you an example, suppose this is my image, right? And my image is 256 by 256, right? And I've got a thing that's like, oh, here's, you know, a line in the image, and then there's another line here, and then it's here, right? And then on the next row down, it looks almost the same as that, right? But shifted a little. You can see how maybe like this could get a whole copy and put it right here, right? Because it's exactly the same, let's say. But if it's 256 and 256, right? Well, this one doesn't matter. But if it's 256 long, well, 256 pixels times 4 bytes per pixel, right, means that we've got 1024 bytes per row, right? So there's no way a 255 look-back window is going to get all the way back to here, because that's a little more than a 1024 look-back already. So typically you want a 16-bit look-back window for images or something in those ranges, because in order to get back to the previous rows, you're going to have to go back that far. For a text compressor, that may not be true. 255 might be a good idea for a text compressor for all I know. But for image data, it's not a great idea. See if there's any other things on compression. Have you ever heard of random seed data compression? No, but that's not surprising because I don't do compression. So there's most most things that involve compression I will not have heard of, if that makes sense. Let me see if there's any more compression questions. Probably more of Jeff and Fabian's territory, but is there generally such a thing as a compressor that compresses a lot and fast? Would some rad compressor leave 10% of initial size and considerably faster than LZ? I guess Bink is hyper fast. Isn't it like live decompression or something? Well, I guess what I would say is, yeah, so there is compressors that compress a lot and fast. The Rad sells a product called Oodle, which is all those compressors, basically. And they actually are the first people that I know of at all who shipped a compressor that is smaller, that typically produces smaller output sizes and typically runs faster than LZMA, right? They did a thing called LZNA, which is significantly faster, but oftentimes as small or smaller than 7-zip. So yes, the Rad compressors are best in class, I guess, at this point, and they've got all kinds of compressors that are super crazy in that way. IEEE 754, I meant block compression that's GPU supported, like BC1 through BC7. You upload the compressed image to the GPU and hardware decodes it when sampled. Yeah, so I talked about this before. I don't like those compressors at all because they're lossy. And when you're doing 2D art, in my opinion, I really care about the quality of the 2D art. So I don't like using GPU compression because it degrades the quality of the image, right? In a 3D game, it's not as big of a deal because you're typically layering a bunch of shaders on top of it, and there's a lot of like layering of textures and stuff. So at that point, it's a little less important to maintain the quality. But I don't love lossy compression. These days, when you've got so much memory to play with, I feel like you've got to really make a strong argument for why you think it's okay to be lossy on stuff, because if you're just doing compression because you saw that there was compression in the hardware and you turned it on, that may be a very bad decision because you'll degrade your image quality, but you don't know that you actually needed what it gave you. You don't know that you needed a smaller size. You don't know that you needed better bandwidth. So you should actually determine that you need those things first before turning it on, because otherwise you're just making a worse looking image. Like that's all it's giving you, right, is a worse looking image. So you need to first determine that you actually needed more bandwidth or more space before turning something like that on, I think. Because otherwise you're basically taking a quality hit and you're not getting anything for it. And even if you do need it, you should first determine that the speed win that you're getting is worth the quality degradation. So at that point, even when you've decided that you might need it, turn it on first, verify that the degradation is not worse than making some other decision, like using less textures or something that you could have done, or less passes or a slightly lower resolution or something, right? So you always want to understand that the texture compression that is in hardware right now is lossy compression. You are taking a quality hit for using it. So first make sure that you actually want that before doing it. Don't just do it, right? Make sure that make sure you understand the trade-offs first and that you're making an educated decision. It's not a hard decision to make because you can just test it both ways and see, at the minimum. So I think we're done here with the questions that I was going to address. So let me go ahead and close this off. All right, so that was just a little forward compression. Like I said, we won't do anything else with that for quite some time. We might return to it when we're done with the game and just want to reduce the size of the asset packs that we ship, for example. We might go ahead and put that in there, if that makes sense. So let's go ahead and and wrap up this stream, and we'll be back after the holiday break with just regular game coding. All right. Thank you so much, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you want to follow along with the stream, you can always pre-order the game on handmadehero.org, and it comes with a source code, so if you want to play around with it, like, for example, if you want to go play around with the compressor and try your hand at doing some compressor tweaks, or maybe learning something about compressor and adding some things to those compressors, that will all be obviously included in tonight's upload, so if you sync with the source code, you will get that and play around with it. We also have a Patreon if you want to support the video series. You can pledge to that. We also have a schedule bot, which I will be rewriting soon to actually work with weekend streams. It doesn't properly mention them at the moment, but we'll fix that. And then we've got an episode guide you can go to catch up on older streams. That's about it for now. I don't know that we will have a stream next week because it is Christmas holiday as is observed here in the States. So most people are off and doing holiday things, so we may skip that one, but we'll be back the week after regardless. So either way, we will see you soon. And until then, have fun programming, and I'll see you all on the internet. Take it easy, everyone.